Exploring how one categorical predictor affects a numeric outcome is another way of saying we are comparing several groups. While ANOVA is a common approach, simple linear regression delivers more insights. Expect to learn how to maximize inference from your model, why famous summary function doesn't provide a very good summary, and what are the best alternatives for it. First of all, it's crucial to visualize the data before modeling, because real-world data often contains contaminations. For instance, in the wage dataset from the ISLR package, I would remove the high-income individuals, earning over 250K per year, not because I'm jealous, but because they are outliers. The data cleaning step is vital and often overlooked. Remember the phrase garbage in, garbage out? If we skip data cleaning, our model's performance could be seriously compromised, and we'll see it in a moment. For now, let's take 100 random people from each educational group and build our linear model around them. To build our linear model, we'll use the intuitive LM function. Within LM, we only need to specify two arguments, the formula and the data. The formula has two sides, left and right. On the left side of the formula, we'll place our outcome, which will come on the y-axis. Unfortunately, this variable goes by several names: response variable, outcome, dependent variable, target, and more. It can get confusing. On the right side, we'll place the predictor variable, which comes on the x-axis. Predictors also have many synonyms: independent variable, explanatory variable, regressor or covariate in linear regression, feature in machine learning, and even risk factor in epidemiology. So many expressions for the same thing drive me nuts. It makes data science seem way harder than it actually is. After building the model, we need to ensure that the assumptions are satisfied. Otherwise, we couldn't trust our model. The performance package offers intuitive and powerful functions to achieve this. For instance, the check posterior predictions function shows how well the model fits the data. The check normality function assesses whether the residuals are normally distributed. And the check homogeneity function compares variances between groups. Looking at the assumptions, I can confidently say that the model fits the data quite well. The residuals fall within the confidence intervals, indicating that our data is normally distributed. Additionally, the variance among groups is relatively consistent. Regarding the remaining assumptions, with categorical predictors, we don't need to check the linearity or outliers assumptions. And we can relax the independence of observations assumption since we don't have repeated measures. And here's why checking assumptions is crucial. When we model unclean data, the model fit deviates significantly from reality. Those affluent individuals, whom I am absolutely not envious of, would compromise the model fit, skew the normality of residuals, and introduce substantial heterogeneity between groups. As a result, I would stop trusting my model. Therefore, it's essential to clean the data before proceeding with modeling. And by the way, if you have a lot of data, and by a lot I mean even as few as 50 observations, it's essential to check assumptions visually, like we just did, rather than relying solely on statistical tests. Why, you ask? Well, statistical tests can sometimes yield significant results, suggesting that assumptions are not met, even when they actually are. Let me illustrate this with an example using the Shapiro-Wilk normality test, which mysteriously detects not normally distributed residuals even when they are perfectly fine. Now that the assumptions of our model are satisfied, we can visualize the model results, specifically the model predictions. To achieve this, we'll use the intuitive plot model function from the sjplot package and provide only three arguments: the model name, the type of predictions, we'll choose effect to create an effect plot, and the name of the predictor we want to visualize. And voila, our plot reveals that salaries increase with increasing levels of education. Nice, right? However, this plot misses three important details. First, it doesn't display the exact estimated averages, leaving us to guess by staring at the y-axis. Secondly, the plot fails to show the precise salary differences between groups. And finally, it doesn't demonstrate whether these differences are statistically significant. To address these issues, people often use the widely known summary function. But honestly, this summary function is not great, and there are much better alternatives available. Instead of explaining every detail of this summary function, which has already been done in numerous videos, I'd like to highlight 9 of its limitations and demonstrate how to overcome them. I truly believe that understanding the flows of the summary function will enhance your understanding of linear regression way beyond simply interpreting the summary output. So please bear with me if the video becomes a little longer. First of all, the summary function doesn't display the estimated averages for all the categories we just saw on the plot. Instead, it only shows the average of the first category, which is now called the intercept. After that, it reveals the differences between the first education group and the other 4 categories. Now, these differences are indeed helpful, but if we want to find out the average salary in a specific group, let's say for college grad, we have to do a little math. We need to add the intercept value of 86,000 to the estimate for college grad, which is 29,000. It's easy but not convenient, because it adds an unnecessary step. Secondly, have you ever wondered why a summary function compares all categories only to the reference category, without comparing categories among each other? Personally, I've never understood that. For instance, knowing whether there is a significant difference between some college and college would help me decide whether to take on more student loans and accumulate more debt. Therefore, the pairwise comparisons among categories, also known as post hoc tests or contrasts, are completely missing. And what about those standard errors we receive instead of the 95% confidence intervals that we actually want? I mean, it's not difficult to calculate confidence intervals from standard errors, but it adds another unnecessary step and underlines the deficiency of the summary function. When dealing with categorical variables, the summary function removes the reference levels of all categorical variables and places them into the intercept. While we should ideally know the reference levels from our data, if we have many predictors, or if someone reads our paper for the first time, crucial information such as the reference level is missing, which is not good. So every time we need this info, we need to dig into the data and look it up. Again, easy to do, but very inconvenient. Furthermore, the scientific notation of p-values just sucks. Most non-statisticians don't understand it, so you need to go to an online scientific notation calculator and translate it, another unnecessary activity. Moreover, the summary function doesn't adjust p-values for multiple comparisons, which increases the probability of discovering nonsense, also known as type 1 error. For all the things it misses, the summary function provides some unnecessary information. For instance, it includes t-values and degrees of freedom, which are rarely discussed in scientific papers. Additionally, the significance stars are redundant, because we already have an exact p-value. However, I must admit, they look beautiful. The summary function makes it almost impossible to interpret interactions. And finally, although the output of the summary function is useful, it is not really pleasing to the human eye and is not suitable for publication. So, if you've ever been frustrated due to similar issues, you are definitely not alone. To address 6 out of 9 issues we've just identified, we can use the tab model function from the sjplot package. This function generates a well-formatted, publication-ready table that not only presents easily interpretable p-values instead of cumbersome scientific notation, but also reveals the 95% confidence intervals instead of standard errors. By setting the show reference level argument to true, we can display the name of our crucial reference level. Additionally, setting the show intercept argument to false removes the potentially confusing intercept term, because we usually don't interpret it anyway, especially in multivariable models. Lastly, the top model function omits unnecessary information and significance stars by default. But if desired, we can gently request significant stars using the p-style argument. Because stars are beautiful and some scientific reviewers appreciate them. And before we tackle the last three problems, let me quickly demonstrate how we can visualize this table using the same plot model function we previously used for visualizing predictions. We simply set show values argument to true instead of using type equals effect, and utilize the with argument instead of specifying the terms and predictor names. This approach will display the model estimates along with their 95% confidence intervals and even include significant stars, exactly what we need. Now, let's get serious for a moment. Comparing levels to only one reference level instead of comparing all categories to each other pairwise seems like avoiding knowledge that is already part of the model anyway. It's like having a lot of money in the bank but not being able to spend it. I never understood why people limit the inference of their models by not comparing all categories to each other. Maybe because our famous summary function does not provide contrasts by default, and it's inconvenient to take an extra step. I could definitely relate to that because I stopped using the summary function the moment I discovered the table regression function from the GTSummary package, which takes only one intuitive argument, add pairwise contrasts to display all pairwise comparisons. The table regression function not only compares all categories with each other pairwise, showing the difference in thousands of dollars between categories, but also corrects p-values for multiple comparisons using the Tukey method by default. This is why the p-value of the difference in salary between high school and below high school is no longer significant. The reason we use Tukey correction instead of the famous Bonferroni correction is that Bonferroni is very conservative, and with many post-hoc tests it can increase the probability of missing a discovery, also known as type 2 error. Having contrast between groups helps us discover that starting college but not finishing it, which is represented by the category some college, does not improve our salaries compared to when we only finished high school. This kind of makes sense, right? Additionally, we can see that obtaining an advanced degree, such as PhD, results in earning of $17,000 more per year compared to completing a regular college degree. So, since this summary function would miss many insights, it doesn't actually provide a very useful summary. And that's where the Imin function from the Imin package comes in. It solves 7 out of 9 of those problems. Within this function, we only need 4 intuitive arguments: the model M, the predictor name education, the pairwise argument for getting contrasts, and the infer equals true argument for obtaining 95% confidence intervals for contrasts and p-values for averages. The results that the Imin function delivers are stunning. Namely, it provides estimated averages with 95% confidence intervals and even p-values, testing the hypothesis that we don't earn $0. These p-values are rarely useful, but sometimes they are. It provides all pairwise contrasts while never leaving out any of the reference levels, and it does not display the pretty useless intercept. By the way, we could even quickly plot contrasts from our results to see where the differences are the biggest. For instance, naturally, the most significant differences appear between the two lowest categories, high school grad and below high school grad, versus the highest category, advanced degree. Additionally, there is no difference between high school grad and not finished college degree. But I digress. Let's continue with the fifth advantage of Imins. It provides humanly readable p-values instead of dodgy scientific notations, and it corrects those p-values for multiple comparisons with the Tukey method by default, so we don't need to ask for it separately. And finally, Imins is so amazing for modeling interactions that I even created a special video on that. And I'll be interested to know how many of you guys have already used the Imins package and what you think of it. Feel free to share your thoughts in the comment section below. However, as much as I love the Imins package, it is not perfect. Specifically, it displays some less useful results, such as standard errors, degrees of freedom, and t-ratios. Additionally, it does not produce a publication-ready table, so that we need to go back to the GT summary package, which not only allows us to enhance our table in different ways, but also enables us to export our stylish table in Microsoft Word or PNG format. This saved me a lot of time and effort while writing a paper. Speaking of time saving, there are two last tips you absolutely need to know about. But before I reveal them, consider hitting the like button if you find this video useful. First, if we need to report equations of our models, writing equations in Microsoft Word format can be quite cumbersome, right? Well, the extract equation function from the Aquatiomatic package converts a model to LaTeX format, making it easier to include equations in your documents. Finally, the last thing I found difficult was to accurately describe model results with sufficient detail. If you have a similar problem, the report package solves it, even if you only use one function to literally report your model. Namely, the report function identifies the type of model you used, shows how well the model fits the data via R², and the general p-value for the entire model. The report function describes where the categories differ significantly from the reference category and which direction, positive or negative, this difference goes. It also shows how 95% confidence intervals and p-values were calculated, and it even interprets the coefficient of determination R². If you wonder how it is interpreted, take a look at the effect size package and literally ask how R² is interpreted. You can also ask how to interpret any value of R² to evaluate model performance. But if you truly want to elevate your data science game, gaining the ability to discover all model performance indicators for any model and check all assumptions with a single function, becoming familiar with the performance package is absolutely essential.